Okay, so this is finally where we get to define the LFP operator that we wanted to define all along. So notice that it takes a type class parameter alpha, which must be a complete lattice. It also takes a function f, because we take the least fixed point of that function, that f. And then we define this fixed point as the infimum of all the a's such that f of a less than or equal a. So this condition here might help to think intuitively as meaning f of a equals a. So you're saying give me the infimum of the set of all fixed points. In this case, it would be the I think it would be the same as the minimum, so the least fixed point. And if we make sure that f is monotone, then we can write it as less than or equal instead. And here we don't require f to be monotone, but later, in the theorems about LFP, we're going to have this requirement, such as here. So why is it written exactly that way? I don't know. I'm not a mathematician or even like a computer scientist who would know this, but doesn't matter. This is just the definition from some textbook, and we've formalized it in Lean. Then we have two technical lemmas that follow from the two properties of complete lattices, right? And finally, we have the so-called Knaster-Tarski theorem, which is a rather fundamental theorem in theoretical computer science. Here we only have the least fixed point part of the theorem, but Knaster-Tarski also covers the greatest fixed point. So it says that for any monotone function f, right, with the emphasis on monotone, LFP is a fixed point and is smaller than any other point. So it's a least fixed point. And this is the proof, which is not particularly interesting, I guess. It uses the two technical lemmas that we introduced above. Yes, and that allows us to finally define our semantics. You see, so the while case here can now use LFP. So this is what we wanted to have all along, and now we have the semantics. And we can apply it to program equivalence. So you might remember from exercise 8 that we had defined a notion of program equivalence based on big step semantics. And now we're going to define it directly in terms of the denotational semantics that we've just introduced. Oh, and notice this is the syntax we're using now, right? And well, first of all, we could prove here that this notion is an equivalence relation, so that it's reflexive, symmetric, and transitive. But all of this we get for free because it's defined in an obvious way in terms of equality, which has all these properties, and then the application of a function, same function on both sides. So we don't need to explicitly state those properties. We're going to get them pretty much for free, but we could. And then next, we proved three so-called congruence rules, which allow us to replace components of programs, right? So here we have a sequential composition of S1 and T1, and we replace S1 by S2, T1 by T2, under the assumption that that we have program equivalence between the S's and between the T's. Same thing with if then else, and same thing with the body of a while. So congruence rules allow us to use a congruence relation or an equivalence relation under under some context, right? So here the context will be the sequential composition here, or it might be this whole context here that allows you to write there, or you can think, well, it's this context here that allows you to rewrite here. And notice how short the proofs are. We do everything just by simplifying using the definition of denotational, program equivalence and the denotational semantics. It's very easy proofs, right? Especially if you compare them with exercise 8, where we had the big step semantics, right? And then you really see the advantage of the denotational semantics. And here are some more examples, right? You have that if you assign x to x, it's the same as doing a skip. And then a sequential composition with skip does nothing. And here we have a more complicated property, which is that the while really expands if we, or contracts, depending on if you read it left to right. So we start with this while, you can expand it in an if then else. If the condition is true, you execute the body and then you enter the while again, and otherwise you do a skip. And the proof of that is more complicated here because we have a while. So let's look into it, right? So it looks messier because you have this LFP, right? But if we use LFP EQ, right? Well, this is exactly what we have here. This is LFP EQ. It's hard to recognize, but it's there. The only thing we have left to do is to show that you know, that this function here is monotone. And we just break it down, right? This is a union, so we apply a union. Then this is a restriction, we apply restrict. Composition, this is a constant. This is the identity. This is a restriction. This is a constant. And that's it. We could imagine writing a tactic using the metaprogramming framework to automate these kinds of proofs here. That would be very easy. So if you had to do many of them. And finally, the very last part of the file is just a proof of equivalence of the denotational semantics and the big step semantics. And this is very optional as usual. And here you see at the end, we're saying that ST is in the semantics of S, big S, if and only if we have a big step transition from big S, small s to T. Right. And now we know that all our semantics are connected, that they all describe the same language, you know, in the same, essentially the same semantics, but using different means. And this concludes part 3 of the course. And in part 4, we're going to look into mathematical applications of theorem proving, starting with the logical foundations of Lean and reviewed from a mathematical perspective. And this lecture will be given by Gabriel.